Hello everyone, and welcome back to the next video on version space search. In this video I will illustrate a new learning method come a search technique with the help of an example. Hope everybody went through the video on concept learning. This is a continuation. Version space search is a continuation of concept learning. In that video I had described a concept of a day configuration, the properties of a day which determines whether that is suitable for a water sport. So here I am going to illustrate version space search with the help of another example, Japanese economy car. So every concept is represented using a certain attributes or features. Here this a car concept is represented using the features country of origin, manufacturer, color, decade and type. So these five features determine which car it is. So here I have included more examples in a table. The column represents a single attribute. The first column is origin, Japan, USA. Those two are the only used values for the feature origin, and the next is manufacturer. Honda, Toyota and Chrysler are the possible values for manufacturer. Next is color. Blue, green, red and white are the colors values used for color, and decades 70, 80, 90s have been used for decade, and type economy and sports have been included in type information. Next is we know in every learning example you have seen in data mining that at the last column it will be the class name to which it should belong. So here in version space search we have a binary classifier or binary search problem where this positive and negative in the last column represent whether that particular tuple or that concept car belongs to the version space or doesn't belongs to. So to train this model we are going to generate a version space which only represents the positive examples and which should never represent the negative example. So here is the example, positive, negative have been represented here. So to construct the model version space, to construct the version space model, first we will be given a set of examples. Some of them will be positive and some of them will be negative. That positive has to be represented in the version space, and negative, whenever a negative comes we should take some of the steps not to represent them in the version space tree. So I took this example in order to get you an idea of what will be a version space, what is a positive example, what is a negative example, what is a concept, what are features, what are attributes. These all are technical terms regarding this version space. Here comes the version space. Version space is a hierarchical representation of the knowledge that enables you to keep track of all the useful information supplied by a sequence of learning examples without remembering any of these examples. So while taking an example we will try to model this version space by including or specifying something or generalizing something. That is, this is actually a hierarchical representation. Starting from the root node we are hierarchically representing the knowledge. Next is version space method. This is a concept learning process accomplished by managing multiple models within a version space. There are two types of models actually. There is a generalization model and a specification model. These are the characteristics of version space. A version space represents all the possible alternative plausible descriptions of a heuristic. That means in a heuristic regarding a concept, which all possible or plausible representations are there that has to be represented in the version space. So there consists of two complementary trees in which one that consists of nodes which are overly general and another tree which consists of overly specific nodes. These are the fundamental assumptions to make a version space tree. The data is correct there are no erroneous instances. There is always the data or the examples we are given is correct. The correct description of a concept is a conjunction of some of the attributes with the values. So always a car is represented using the country in which it's originated, Japan, then its color and its evolution decade, its type and the company, so manufacturer. So these are the attributes which are always in conjunction to decide the concept. So these are the diagrammatic guidelines. To construct a tree, we have certain guidelines. There is generalization tree and a specialization tree. Each node is connected to a model. So we are trying to make a model or a tree which represents our original examples. Positive examples, not the negative examples. So nodes in the generalization tree are connected to a model that matches everything in subtree. And nodes in specialization tree are connected to a model that only matches with only one thing or one concept in subtree. So link between nodes and their models denote generalization relations in a generalization tree and specialization relations in a specialization tree. So we will see about this tree details, complementary trees, in next slide. So this is a diagram of version space, and in this the specialization tree is colored green and generalization tree is colored red. And we can see the red color node starts in the beginning, and that single node in the beginning is known as a root node of the generalization tree, the most general model that matches everything. This is how we can represent a concept which matches everything. That will be always simply question mark for every attribute. That is, anything may come for, any value may come for the first attribute, and any value may come for second argument, and so on. So the first node, the root node, matches everything in the model. Then next comes the specialization. Each branch is used to specialize any of the attribute. There are 5 attributes for our concept car. So 5 branches are there. Each branch represents specialization of each attribute. So here it is. Now comes the next level, comes the positive instances which prove the general description. So the second level are using negative instances which specialize general descriptions. That is, when negative instance come, we need to avoid them in the version space. So we will specialize those we need to represent. So whatever there is in negative instances we must exclude, and whatever we have in positive instance we should include. So we will specialize the general description by excluding that negative instances. Then in the next level, in third level, comes positive instances which prove the general descriptions. So when a positive instance comes, we can decide visual further branches. Generalizations are not needed. Those branches can be cut off. So while discussing this theory portion, you will not be able to follow it very well. When we discuss it with an example, you will be able to, at the end it comes the example. At the end we will discuss an example which will help you to understand this concept very well. Suppose you are not understanding it, directly go to the example and compare it with the theory. Now from downward side, the last node is the specification tree root. The most specific model matches only one thing. That will be exactly a single car model. A single car model with all the values in the question mark position. So sometimes might be Japan, then manufacturer is Toyota, then color is red. So that might be a single one. Then positive, when a positive instance come, we can generalize those specializations. So simply a single concept is represented here. We have 5 different branches to make generalization. So whatever can be generalized, to represent a positive instance can be included there. Then whenever a negative instance come, those generalizations which never lead to a negative one. So suppose we want to eliminate a negative example, or we need not to represent a negative example. So whenever a negative example comes, we just need to prune those specific descriptions which we have given here. So in between, eventually these positive samples and negative samples may force the general and specific models to converge to a solution. Then comes generalization and specialization. The key idea in version space learning is that specialization of the general models and generalization of the specific models may ultimately lead to just one correct model that matches all the given positive examples and doesn't match all negative examples. That means, suppose we are giving a new example to a version space tree constructed to match a model, it should only be able to find a match with the positive examples only. So whenever a negative example is given, it should not match with any of the branches of the tree. That's it. Then I think you very much know what is generalization and specialization. We have learned in predicate logic that generalization means there is for all x simply represents general. For everything, general means that everything comes inside. What about specialization? Suppose we have a for all x. For all x, all men are mortal. For all x, m of x. X is men. So any men is represented using the variable x. So that is a generalization statement. For all. For all is actually generalization. Then what is specialization? Specialization meaning that giving a particular value for x is known as specialization. So in predicate logic, the same statement all men are mortal can be revised as Socrates is mortal. So that can be represented using m of x is replaced using Socrates. So that means Socrates only is mortal. So specialization is simply for a particular value only and generalization for a set of variables. So here the variables are represented using question marks, not x, y, z or anything like that. If general, we will represent that particular attribute to be question mark. Okay, so that is the key idea in version space learning. So version space method learning has a candidate elimination algorithm. This algorithm describes how we can construct a version space from a given set of positive and negative examples. So it handles positive and negative examples symmetrically. Given a representation language is there for the concept. In our example, in brackets, different attributes are given. That is the language we use. A set of positive and negative examples expressed in that language. So here the tuples I had shown in that previous table represent our positive and negative examples. Then we compute a concept description that is consistent with all positive examples and inconsistent with negative examples. That means whenever a new positive example comes, the created model should find a match with that positive example, and whenever a negative example comes, it is inconsistent, meaning that there should not find a match with any of the subtree or any of the nodes in the subtree. So here is the candidate elimination algorithm. So we start with two sets, one named G and another named S. G is maximally general hypothesis, that is G represents generalization tree, that is which we have represented using red color, and S is for specific hypothesis, that is for specialization tree. So this G contains only one element in the beginning initially, that is a null description, that is which matches all features, all the variables, which matches everything in the set. Then S is for simply one element, one concept, one example, that is the first positive examples. So here I have represented this in red color and green color, which represents the node itself in the version space tree. Red for generalization and green for specialization tree. Then the algorithm was as follows. It can accept any number of samples one after another. While considering one training sample example, it check whether this is positive or negative. We know the last column of this description is positive or negative. I had shown the example in the beginning itself. If the example is positive, we need to generalize all the specific model to match the positive example. So positivity, when a particular concept belongs to a class, it should be find a match, then it need to be more general. So by ensuring the new specific model involve minimal changes, and each new specific model is a specialization of some general model, and no new specific model is a generalization of some other specific model. And also another step in considering a positive example is to prune away all the general models that fail to match the positive example. So first generalize the specific model, then prune away all the general models. In the case where the negative example comes, we need to specialize all general models, and while doing that, ensure that the new general model involves minimal changes, very small changes. The new model is a generalization of some specific model, and no new general model is a specialization of some other general model. And also another step is prune away all the specific models. So these two are contradictory words, vice versa. And at the end, how to end? So whether this is a success or failure or consistency or inconsistency, that will be determined by comparing S and G. If S and G are both singleton sets and they are identical, then output their value and hold. That means our construction is over and version space can represent all the possible models, plausible models. Then if they are different, the training cases were inconsistent, output this result and hold. Else, continue accepting new training examples and proceed. So this is the algorithm for candidate elimination. This algorithm stops when it rounds out of that data. That means all the examples have been considered. That's the first case. The number of hypotheses remaining is 0, 1 or 2 plus. There is no consistent description of the data in the language. 1 means here comes the answer for our searching, and 2 plus means all descriptions in the language are implicitly included. These are the some of the properties, advantages and disadvantages of version space search. I suggest you to do self-study on this matter. And here comes the problem. First problem, I plan to discuss two problems. This is problem 1. This I have already explained in the beginning itself to discuss about concept. This problem is known as Japanese economy car. So we have 5 features: origin, manufacture, color, decade and type. And these are the data we have been provided to construct version space search. Japan Honda Blue 1980 economy is the first concept or the first example, which is positive example. And then second, third, fourth and fifth, 5 possible examples are given. So we consider one example in turn. So the first example here is positive example. So consider the first positive example, Japan Honda Blue 1980 economy. So here we initialize G to be a singleton set that includes everything, which is a null description. G is equal to everything question mark. That means it can include, find a match with anything. Then S is a singleton set that can find a match only with the first positive instance that we have considered here, that is Japan Honda Blue 1980 and economy. Here comes the generalization tree in red color and specialization tree in green color. So these models represent the most general and most specific heuristics one might learn. Most general means that can accommodate anything, can find a match with anything. Most specific is green color, that means it can accommodate only one car having the specifications Japan, Honda, Blue, 1980 and economy. So the actual heuristic to be learned, Japanese economy car probably lies between these two. So we need to add more negative examples and positive examples. This is the next example, next tuple we had in the table. Negative example is Japan Toyota green 1970 sports. So when the example is negative, the algorithm says to specialize generalized table, generalization tree. So specialize G to exclude negative example. So now G is, in the previous example, G is completely general, that means it can accommodate any example. So this is a negative example, that means we should avoid Japan, Toyota, green, 1970 and sports. That means we can do only by specializing some of the concepts here. That means the previous example itself has a Japan, so here also Japan, so we cannot specialize Japan because positive example, previous example also has a Japan, so we cannot specialize. So the first one is always question mark in 4 tuples. Then second, Toyota is negative, but positive example shows Honda is positive, so it need to specialize Honda. Then green is negative, but blue is a positive, so blue can be specialized. Then 1980 is positive, 1970 is negative, so I can specialize 1980. Anything with 1980 has to be accepted. Then sports has to be accepted, exempted or excluded, but economy has to be added or has to be find a match with. So these are the specializations we have done in G. Now there is no generalization here and nothing pruning also, because only one node is there in specialization tree. So this is the resultant tree. Generalized node, root node is specialized to 4 different. Then the first option, Japan, is not specialized because the previous positive example has Japan. So here is the next example, positive example. So when a positive example comes, we need to generalize yes to include positive example. So the green tree here is generalized to Japan and generalized to question mark because Honda is a positive instance and Toyota is also a positive instance. So anything that come in the question mark position has to be included. Then blue is already there. Both the cases, positive case has blue, so that is specialized. No need for generalization. But 1990 is the decade in positive case here, but 1980 is already there. So anything 1980 or 1990 comes, this question mark can accept both the cases. Then economy is specialized. The type is economy here, and in the previous positive example also it is economy. So we can generalize it by doing Honda position, that is manufacturer and decade can be generalized. And also another step in coming a positive example is to prune G, that is we have 4 different branches or successors for the root node of generalization tree. So we can prune G by considering here Honda is specialized, so whatever has been generalized here has to be pruned out. Here Honda has been generalized because Toyota has to be accepted, and also 1980 cannot be specialized because 1990 comes in positive case. So whatever has been generalized here has to be exempted from generalization tree. So these are the resultant trees. Next example is negative, USA Chrysler Red 1980 economy. Here is negative, so we need to specialize G. The specialization of G comes like this. It should exclude the negative example, but it should be inconsistent with yes. In the previous table, question mark, can accept anything, that is Japan or USA or anything can be accepted. Here also Japan or USA can be accepted. But in this case, Japan comes. When Japan comes here, this is blue, so it cannot be accepted. So this is a negative example. This first tuple or the first generalization concept accept or is inconsistent with the negative example. But when the second example, the first one is question mark actually in the previous case, that is this is question mark, question mark, question mark, question mark. That is whatever USA or crystal or red or 9080 anything come here, it will be accepted, and here it is economy, so it will be accepted. But we need to exclude it by just changing or specifying USA comes here, but only Japan need to be included. USA cannot be included. So by specializing this question mark to Japan, we can change or specialize G. So that's the change we have made. There is no pruning regarding specialization tree here, because Japan specialized this specialization tree never accepts this one because the color is blue and the country is Japan. Next example, the last example is positive example with Japan, Honda, White, 1980 and economy. When a positive example comes, prune generalization tree G to exclude descriptions inconsistent with positive example. So here Japan, Honda and White, this tree never accept this branch never accept this positive example, so we can prune it off. And also here Japan, Honda, White, 1980 economy will be accepted here and also here. So this tree need to be maintained. But the specialization, generalize yes to include positive example. Here some more generalization is needed. This Japan, then question mark can be accepted, Honda can be accepted, but White cannot be accepted here because blue is specialized. So we can change this specialization blue to the question mark, which is again generalization. And 1980 is generalized, so anything will be accepted. Then economy is here, which is specialized. So by changing blue to question mark, we can make this positive example consistent with this tree S. So this is the final decision. Japan, question mark, economy is added here. That is the specialization of generalization tree, and the specialization tree is generalized to get into Japan, question mark, economy. So this is the final view. Here G and S are singleton sets, and that was the condition we had checked in the method invocation or candidate elimination algorithm. S is equal to G. That means the algorithm converges to a proper version space. So no more data in our table, so the algorithm stops, and this is the final version space generalization tree. And generalization tree, the redrawn, this has been simply redrawn to find it in the structure. Generalization tree, which is specialized up to this level, and specialization tree, which is generalized up to this level. So both are same, and so this is the final version space which can accept any of those samples. Next problem is regarding the same concept with 2 or more examples added in the table. So up to the 5th row, the same data have been provided, and we need to take the 6th example. 6th example is a positive example. That means we need to accommodate Japan, Toyota, green color. So we had not taken green, right? So green color, we have to check the last node of this tree to check if accepted. This is accepted here. So Japan with the economy, Japan, Toyota is accepted, green is accepted, then 1998 economy is accepted. So the last node Japan, Toyota, green, 1980 is accepted. So here also both are same. So this will be accepted. So there is no problem inconsistency with the version space and the positive example, so we need not to do any specialization here to accept this positive example. Then last one is the negative example. Here by checking this Japan Honda red 1990 economy, actually this generalization tree and specialization tree can accept this or can include this negative example, and no specialization is possible. That means Honda and Toyota has to be accepted here. Already positive example contains Honda, and by putting red here we cannot generalize. Red, green and positive examples contains more than one color, so we cannot specialize using any other color. 1970 and 1980 comes in positive example, so we cannot specialize with 1990 or 1980. So it cannot be specialized further or generalized further to exclude negative example. That means the version space collapses. We cannot reconstruct this version space to exclude this negative example now. So the conclusion is that no conjunctive hypothesis is consistent with this data set. The problem is found with the last data item. So we stop here. We cannot construct a version space which would accept the positive examples in it but exclude the negative examples. That means the version space collapses. Thank you everyone. Hope to see you in the next lesson.